Welcome back. This is video 2 of lesson 6.2 for Algebra 2. Alright, let's talk about like radicals. Two radical expressions with the same index, so the same kind of root. They're both either cube roots or fifth roots or square roots or fourth roots. They're just the same and the same radicand. So you're taking the whatever root you're talking about, cube root, fifth root, of the same value. Okay, what's inside the root is the same. Alright, so we're going to add and subtract like radicals and roots. So we want to simplify fourth root of 10 plus 7 times the fourth root of 10. Okay, so we've got the same index of 4, and our radicand is the same, 10. So we've got 4 square root of 10, and we're going to add 7 times 4 square root of 10. We've got 1 of something plus 7 of that same thing, and so we have 8 fourth roots of 10. All right, we've got 2 times 8 to the 1/5 plus 10 times 8 to the 1/5. Well, having 1/5 is the same thing as taking the fifth root. So since they're both 1/5 and they're the 1/5 power of 8, we have like expressions, and so we can just add them together. So 2 plus 10 times 8 to the 1/5 power is 12 times 8 to the 1/5 power. Alright, this next one, we've got the cube root of 54 minus the cube root of 2. So they're both cube roots, but we've got a 54 and we've got a 2. So the radicand's not like. Well, here's the deal. We need to first make sure they're both simplified. 54 equals 27 times 2. 27 is a perfect cube, so we can actually keep working with this one. 54 equals 27 times 2, so we can write cube root of 54 is cube root of 27 times cube root of 2. And then we just copy our minus cube root of 2. Cube root of 27 is 3. 3 cube roots of 2 minus a single cube root of 2 is equal to 2 cube roots of 2. Okay, let's talk a little bit about variable expressions. The properties of rational exponents and radicals can also be applied to expressions involving variables. Because a variable can be positive, negative, or 0, sometimes absolute value is needed when simplifying a variable expression. When n is odd, the nth root of x to the n equals x. When n is even, the nth root of x to the n is equal to absolute value of x. Absolute value is not needed when all variables are assumed to be positive, which is what we're going to do. Okay, and here's, just so you understand, here's why. If I've got the 7th root of 5 to the 7th power, that's going to equal 5. If I've got the 7th root of negative 5 to the 7th power, that's going to equal negative 5. No worries there. If I have the 4th root of 5 to the 4th power, that equals 5. But if I have the 4th root of negative 5 to the 4th power, when I do negative 5 to the 4th power, I get 625. When I take the 4th root of that, though, I get positive 5 back. And so that's why if we don't make the assumption that all variables are positive, we're going to have that those absolute value bars. All right, we're going to simplify the expression and assume all variables are positive, which is awesome because we don't have to worry about when to use absolute value bars and when not to. All right, we've got the cube root of 64, y to the 6th. 64 is equal to 4 cubed. Y to the 6th can be written as y squared to the 3rd power. Anything raised to the 3rd power there, we're going to be able to cancel the cube with the cube root. And so we're going to get 4y squared. We've got 27p cubed to the 12th all to the 1/3 power. It's the same thing as taking the cube root, so it's essentially the same kind of problem. So we've got 27 to the 1/3 power, p cubed to the 1/3 power, cubed to the 12th to the 1/3 power. 27 to the 1/3 power is 3 because it's the same thing as cube root of 27. We've got p, and then we've got a power to a power. We've got p to the 3rd power to the 1/3 power. So we're going to multiply those exponents. So we've got p to the 3 times 1/3. And then we've got the same kind of situation with q, but we've got q to the power of 12 times 1/3. 3 times 1/3 is just 1, so we have 3p because that exponent of 1 is left to be understood. 12 times 1/3 is 4, so our final answer is 3p q to the 4th. Okay, For c, we've got the fourth root of m to the fourth over n to the eighth. So let's go ahead, we'll just do fourth root of m to the fourth and then fourth root of n to the eighth. So let's rewrite n to the eighth as n squared to the fourth power. We want the 4 on the outside of the parentheses there because we're taking the fourth root. In case you're wondering, well, how do you decide which goes on inside, which goes on outside? We're wanting to get rid of that fourth root, so we need that fourth power on the outside of the parentheses and n squared on the inside so that we can do our canceling. Fourth root of m to the fourth is just m. Fourth root of n squared to the fourth, power of 4 and root of 4 cancel, and so we just have n squared. So we have m over n squared. Okay, we've got 14x times y to the 1/3 power all over 2 times x to the 3/4 power times z to the negative 6. So 14 divided by 2 is 7. X divided by x to the 3/4 means we're going to have x to the 1 minus 3/4. We have y to the 1/3, and then if we bring z up to be on the same level as everything else, we need to take the opposite. We need to take away the negative. In other words, we're going to have negative 6. And so we have z times x to the 1/4, because 1 minus 3/4 is 1/4, y to the 1/3, and then z to the 6th. Okay, our last example, we're going to write the expression in simplest form, assume all the variables are positive. We've got the fifth root of 4 times a to the 8th times b to the 14 times c to the 5th. So we want to factor out perfect fifth powers. Now 4 is just equal to 2 squared, so there's really nothing we can do about that. A to the 8th, we want to break off perfect fifth power. So we can break off a to the 5th. 8 minus 5 is 3, so that leaves us with a to the 3rd. B to the 14th we want to break up as b to the 10th because that is divisible by 5, that exponent. And then that leaves us with 4 more powers of b, so we have b to the 4th, and then c to the 5th, it's a perfect fifth power. Now, we're going to use the product property, and everything that's a perfect fifth power we're going to bring out front. So we're going to have fifth root of a to the 5th times b to the 10th times c to the 5th. And then we're going to have times fifth root of whatever's left over. So we didn't bring out the 4, so we're going to have the 4, the a cubed, and the b to the 4th. And we're going to simplify. Okay, so the easiest way to do this, okay, this first fifth root right here with a to the 5th, b to the 10th, c to the 5th, is go 5 divided by 5 just gives me a to the 1st. That just gives me 1. 10 divided by 5 is 2, so I'm going to have b squared. C, I have 5 and c to the 5th, so that's going to cancel completely with the fifth root, or 5 divided by 5 is just 1, so I just have c, which is the same thing as c to the 1st power. And then I just have my fifth root of 4 times a cubed times b to the 4th. All right, I've got the cube root of x over y to the 8th. Alrighty, I can't leave that y to the 8th in the denominator, so let's try to make the denominator a perfect cube so that we can not have a radical in our denominator. So we had y to the 8th. Y to the 9th is the very next value that's divisible by 3. So if I take y to the 8th and I multiply it by y, or y to the 1st, that's going to bring me up to y to the 9th. So if I do that on the bottom, I have to multiply by y on top as well. And so I'm going to have the cube root of xy over y to the 9th, because 8 plus 1 is 9. So now let's do cube root of the top, cube root of the bottom. So cube root of xy is just cube root of xy. Cube root of y to the 9th is y cubed. And again, kind of a shortcut way of doing that is 9 divided by that index of 3 is 3. So that leaves me with y to the 3rd power. Okay, guys, thanks to Larson Algebra 2 from Hope McDougall. Make sure you try the practice problems, the problems to try on your own. We'll check them when you come to class next time, and then you'll get started on your rounds. Have a good day. I'll see you soon.